Hi, my name is Publio Silva and today I'm presenting you a machine learning model to classify the feature model maintainability. This is a collaborative work with Carla Bezerra from Federal University of Ceará and Machado from Federal University of Bahia. The feature model is an artifact that describes all the features of a software product line and the relationships and constraints between them. In general, the changes that an SPL undergoes over time also imply changes in the feature model. Therefore, this artifact can become very complex over time, which makes the evolution and maintenance of the SPL difficult. This is why it's so important to assess the maintainability of the SPL from the earliest stages of the SPL development lifecycle. Assessing the maintainability of the SPL from the beginning allows taking corrective actions, which prevents problems from spreading across the entire SPL. As the feature model defines all SPL features, it is possible to make this evaluation using this artifact. Now, how to assess the feature model maintainability? One of the commonly used strategies to carry out this assessment is to use quality measures. However, this strategy has some flaws. The first is that each measure focuses on a specific aspect of the quality of the feature model, which makes a more general assessment difficult. Another is that, in general, the range of values is wide and there may not be a clear indication of which values can be considered good or bad. Also, the greater the number of measures to be evaluated, the greater the effort required to carry out the evaluation. Therefore, some works use different techniques to add quality measures to overcome the mentioned problems. In a work by Oliveira and Bezerra, for example, the authors used fuzzy logic to aggregate several quality measures in order to generate a single quality index for the feature model. This image shows the 5 ranges of the feature model's maintainability index, which are very low, low, medium, high, and very high. In our previous work, we used unsupervised machine learning algorithms to aggregate quality measures and classify the maintainability of the feature model. We used clustering algorithms, and this image shows the feature model clusters separated by maintainability. In our previous work, we investigated the use of machine learning techniques to assess the maintainability of feature models. We chose to use unsupervised machine learning algorithms because this type of algorithm does not require a labeled training dataset. Our previous work and the work of Oliveira and Bezerra were able to assess the maintainability of the feature model. However, none of the works were able to provide indications of what could be done to improve the quality of the feature model. With that, we had 2 things in mind when doing this work. The first was to be able, like previous works, to assess the maintainability of the feature model. And the second was to allow domain engineers to use the evaluation results as an indication of what they need to do to improve the quality of the feature model. So, the goal of this work is to use machine learning algorithms to classify the feature model maintainability. The quality measures being the independent variables and the maintainability classification being the dependent variable. As the dependent variable is categorical, we used classification algorithms. We decided to use only white box algorithms because with this type of algorithm it is possible to interpret and explain the machine learning model results. To guide our investigation, we defined two research questions, which are: what are the most representative measures to evaluate the feature model maintainability, and what is the best machine learning model to evaluate the feature model maintainability? Now, let's dip into the study steps. The first step was to collect the data to train the machine learning models. We collected 342 feature models from the Splot repository. These feature models had between 10 and 290 features. We also chose the measures from the Minicoff catalog as our initial set of independent variables. This is a catalog that defines 15 maintainability measures for feature models. We also chose the DyMMer tool to collect the 15 measures for each feature model in a dataset. We chose the DyMMer tool because we already knew it and because this tool supports all 15 measures in the Minicoff catalog. This is a screenshot of the DyMMer tool. As you can see, the tool supports modeling feature models for conventional software product lines and dynamic software product lines, and it also calculates quality measures for feature models. To train the classification algorithms, we needed a labeled dataset because it is a type of supervised machine learning algorithm. We could label the dataset using only SPL experts, but would be difficult to get a good amount of experts. So we take a little different approach. We found two approaches in the literature to automatically classify the maintainability of feature models, which are the Oliveira approach from the work of Oliveira and Bezerra, and the Silva approach from our previous work. So we used both approaches to classify the entire dataset, generating two new datasets, one classified with the Oliveira approach and another using the Silva approach. After this, we take a subset of 50 samples from each dataset. We also classified the subset manually using 15 SPL experts. So we compared the classifications of the Oliveira and Silva approaches with the classification of the experts in three parameters, which are accuracy, pessimism/optimism, and distance. In the end, the Oliveira approach was the closest to the experts' classifications, so we used the dataset classified with the Oliveira approach to training the machine learning models. The next step was to select the independent variables. This step helps to reduce the dimensionality of the problem, making the machine learning models more simple. We used two strategies to select independent variables. In the first strategy, we used the Spearman's correlation, and in the second strategy, we use the independent variable importance for a machine learning model. In the first strategy, we selected measures whose correlation was equal to or greater than 0.6 and obtained 6 measures. In the second strategy, we used the logistic regression algorithm and obtained 7 measures, and the decision tree algorithm and obtained 9 measures. This is an example of the second strategy using the decision tree algorithm. It can be seen that only 9 measures are important to the decision tree algorithm. We used the 3 sets of measures in different machine learning models, and the set of measures that generated the best results were obtained by analyzing the importance of independent variables for the decision tree algorithm. So we chose the set of 9 measures. The next step was to train and evaluate the machine learning models. We chose 3 white box algorithms, which are naive Bayes, logistical regression, and decision tree. We also chose 5 classification metrics, which are accuracy, precision, recall, F1, and AUC-ROC. To verify that the machine learning models were generalizable, we also performed a 10-step cross-validation. This is the result of 10-step cross-validation for accuracy, precision, recall, F1, and AUC-ROC metrics. As you can see, the decision tree model got the best result for all 5 metrics. The decision tree model was the best classification model with accuracy, precision, and recall of 0.81, F1 of 0.79, and AUC-ROC of 0.91. So it is possible to say that in this work we obtained better results than in our previous work, where we obtained an accuracy of 0.61 and a precision of 0.7. It is not possible to make the same comparison with the work of Oliveira and Bezerra because accuracy or precision values are not provided. The decision tree model generates a binary decision tree to make classifications. This is a simple example of a binary decision tree. In this example, if the flexibility of configuration measure is less than 0.5, the result will be bad. Otherwise, the result will be good. This tree can be used to interpret the results of the machine learning model and improve the quality of the feature model. In this example, to improve the quality of the feature model, just make the flexibility of configuration measure greater than 0.5. The binary decision tree can be really big, so to help with this process, we created a web tool that classifies the maintainability of the feature model and also analyzes the binary decision tree to provide suggestions for changes in the values of the quality measures in order to improve the quality of the feature model. In this example, the feature model already has good maintainability, but it is still possible to improve it by making the measure number of top features less than or equal to 3.5. So for the first research question, the finding was that the measures most representative to evaluate the feature model maintainability are SCDF, COGC, RDEN, NM, FOC, NTOP, NLEF, NF, and DTmax. Among these, NF and DTmax stand out as the most representative. For the second research question, the finding was that the best machine learning model to classify feature model maintainability is the one that uses the decision tree algorithm. Here we discuss some threats to validity. To mitigate threats to internal validity, all data was collected in an automated way using the appropriate tools. The main concern regarding construct validity was when selecting the appropriate independent variables. To mitigate threats of this type, we used 2 independent variable selection approaches and test each set of measures obtained, finally selecting the one that maximizes the accuracy of the machine learning model. To mitigate threats to external validity, we used a dataset composed of feature models of different sizes and characteristics. We also performed a 10-step cross-validation to ensure that the results can be generalized. To mitigate threats to conclusion validity, we used 5 classification metrics that analyze different aspects of the machine learning model, and also performed a 10-step cross-validation. Among the main contributions of this work, we highlight the following. Compared to feature model maintainability classification approach described in the literature, create a machine learning based approach to classifying the feature model maintainability using white box algorithms. The best machine learning model had an accuracy, precision, and recall of 0.81, F1 of 0.79, and AUC-ROC of 0.91. Find out the 9 most significant measures to assess the feature model maintainability, and create a web tool to assess the feature model maintainability and help interpret decision tree model results. As feature works, we can point out using the information extracted from the decision tree model to create a mechanism capable of providing suggestions for improving the feature model maintainability. That is, a mechanism capable of suggesting changes in the structure of the feature model to improve maintainability. Make more adjustments and optimizations in the hyperparameters of machine learning algorithms to increase the quality of the machine learning models obtained. And using agnostic model approach to measure the importance of variables in the selection of independent variables. Here you have the link to the GitHub repository where you can find all the resources of this work and the link to the web tool we created. Here you can also see the email address for contacting the authors. Thank you for your attention.